The rational zero theorem is an incredibly powerful tool for finding some of the zeros of a polynomial and allowing us to break it down at least part way in order to hopefully ultimately be able to completely factor it. You might be wondering, does it always work? And the answer is no, because it's limited to polynomials that have integer coefficients, and it's limited to finding rational zeros. So if I had a high degree polynomial and lots of its zeros were irrational or non-real, the rational zero theorem isn't going to help me find those. Okay, so it's not a guarantee that I'll be able to solve any polynomial problem or be able to completely factor any polynomial. I do have some theorems up here on the board, though, that essentially say that all polynomials factor. We may not always have the tools to be able to figure out how they factor, but they do. Okay. So we start with the fundamental theorem of algebra. That makes it sound really important, and it is. Okay. And it says this: if f of x is a polynomial of degree n, where the degree does have to be 1 or bigger. If the degree is 0, remember that's just a constant polynomial. And so, if I have f of x equals 2, it's always 2. It doesn't have any zeros. Okay. But if the degree is 1 or bigger, and we're allowed to have complex coefficients, we're not actually looking at anything that complex. We're always looking at polynomials with real coefficients, but this theorem applies even if I had complex coefficients. Okay. Then this says that f of x has at least one complex zero. There's guaranteed to be at least one zero. And of course, because zeros correspond to factors, that's going to mean that we can at least partially factor f of x. And then the linear factorization theorem says, well, we can do more than partially factor it, we can completely factor it. So with the same conditions on f, it's degree 1 or bigger, and it's got complex coefficients, and here I've just written it out in standard form. This theorem says that we can completely factor f over the complex numbers into a product of linear factors and then one constant factor. If my lead coefficient is some number other than 1, then if I look at all of these factors of x minus a 0, x minus a 0, x minus a 0, that would give me something with a lead term of 1. I need to multiply by my lead coefficient, a sub n, in order to get the right lead term. Okay. But basically, I can factor this into one constant and then n linear factors, which would just have the form of x minus a 0. So I've made a note here that these numbers c1, c2 through cn are the complex zeros. You'll notice I'm not assuming that they are necessarily distinct. C2 might be the same as C1, then I would have a 0 with multiplicity of at least 2. Okay, so that's perfectly acceptable. Okay. Now, this theorem actually follows from the fundamental theorem, and I want to just walk through how we can see that by reviewing the last example that we did in the previous video. So we started with f of x was equal to 3x to the fourth minus x cubed minus 36x squared plus 60x minus 16. Now, that polynomial has complex coefficients. They all happen to be real, but remember, the real numbers are just a subset of the complex numbers. Its degree is 4, so the fundamental theorem applies. I know that this has at least one zero. Now, we were lucky, it had at least one rational zero. So we used the rational zero theorem and tried things out, and we found that 2 was a 0. So once we found that 2 was a 0, we knew that x minus 2 was a factor, and so we were able to partially factor this. We wrote it as x minus 2 times 3x cubed plus 5x squared minus 26x plus 8. Excellent. Now, this is a polynomial of degree 3. It has complex coefficients. Again, they happen to all be real, but that is included in the complex numbers. So now I can apply the fundamental theorem of algebra again. I know that this has at least one real zero, one complex zero. And we were fortunate in that we found again, we happened to find a rational one. So I've got x minus 2. Now, if this has a 0, there's going to be a corresponding factor. Now, we found that 2 was actually a repeated 0, And then we were able to factor this even further. And then we got 3x squared plus 11x minus 4. Now, this is a quadratic. This is a polynomial of degree 2. We still have real coefficients, which counts as complex coefficients, so the fundamental theorem applies again. This has to have at least one zero, which means that we can factor it. And we were actually able to factor this not by just finding the zeros, but by actually just doing some sort of trial and error to factor this. But I know because there's a zero, there's going to be a corresponding factor, and I can factor it further. So we ended up getting x minus 2, x minus 2, 3x minus 1 times x plus 4. And note this, I could rewrite if I wanted to as 3 times x minus 1/3. So that matches the format then that we had in the linear factorization theorem. We've got one constant factor, which matches the lead coefficient, and then all the other factors are just x minus a zero of the polynomial. So that's pretty powerful, and the theorem tells me that given any polynomial with complex roots, it can be completely factored. But if we're not able to find all of the zeros, we might struggle to actually do that factoring. Okay, so the rational zero theorem gives us a finite list to check, but it's only a finite list of the rational zeros. So if I had a polynomial that had 10 non-real zeros, I'm probably going to really struggle to factor that. I do want to just remind you, though, of a couple of techniques that you can use in trying to factor. Okay? So when we've got a big polynomial, rather than saying, can I factor this using my factoring skills, we often say, let me try to find a zero. If I find a zero, then I find a corresponding factor, and I can break it down. But sometimes the factoring skills that we have should actually be our first step. Let's suppose I had f of x equals x to the fourth plus 5x cubed plus 4x squared. Okay. Well, here, I couldn't use the rational zero theorem to start looking for zeros because my constant term is 0. And remember, to use the rational zero theorem, I have to have a non-zero constant. But if my constant term is 0, that's going to tell me that there are x's in every single term. So that there's a greatest common factor, which in this case would just be x squared, that I can pull out. So I can say this is x squared times x squared plus 5x plus 4. That's factoring that I can do without finding the zeros first. Okay? And then I can probably factor this even further. I think I can unfoil that. That's just going to be x plus 4 times x plus 1. So often, using the rational zero theorem and synthetic division to find the factors that correspond to zeros is helpful when I have a very big polynomial. But make sure you look, if you don't have a constant, if you don't have a non-zero constant term, you've got to start by just factoring out the biggest power of x. Let me give you another example where the rational zero theorem isn't necessarily going to help us, but the factoring skills that we have coming into this class will help us. Let's suppose I had f of x equals x to the fourth plus 3x squared plus 2. Okay. Now, I could certainly create a list of possible rational zeros, but I'll tell you right now, none of them are going to work. This is a polynomial that has all non-real zeros. Okay. So, now I know that because I created the problem. Shouldn't necessarily be obvious to you at this point. But notice that it just has 3 terms. I might be able to factor this by unfoiling it. Now, it's not a quadratic, but that's x squareds, and x to the fourth is just x squared squared. If I recognize that, I can hope that I could factor this with my first terms being x squared and x squared. My last terms would have to multiply to give me 2, so I'm thinking 1 and 2. They've got to have the same sign, looks like both positive. Let's see if that worked. X to the 4th plus 2x squared plus x squared is 3x squared plus 2. Fabulous. So we have factored this into 2 quadratics. Now that would be as far as we can factor it over the real numbers, because both of these would be irreducible over the reals. I can see that because in order to make this 0, x squared would have to be negative 1. In order to have x squared be negative, I've got to be working in the complex numbers, including some imaginary parts. Same thing here. In order for this to be 0, x squared would have to equal negative 2. So if I were factoring over the real numbers, I would stop here. If I were factoring over the complex numbers, I'd break each one of these up into linear factors. So here, this would be x plus I times x minus I. Because, of course, the 2 zeros would be, if I got x squared has to equal negative 1, I would get x has to be plus or minus the square root of negative 1, which is I. Okay. Same thing here. If x squared would have to equal negative 2, x would be plus or minus I times the square root of 2. So I'd have x plus I root 2, x minus I root 2. So this would be completely factored over the real numbers, and there would be no real zeros. This would be completely factored over the complex numbers, and there would be 4 complex zeros. I root 2, and negative I root 2. And notice the only way we're going to get there really is if we recognize that we can unfoil this to begin with. So very often the rational zero theorem is going to be a place that I want to start, but don't forget you do have some other factoring techniques as well. Look for when those might be useful too.